It's still linear optimization, so the principles and understanding of things that we're doing, is kind of the same. It's just a little bit different kind of a problem in that what you are doing is using some binary variables that have an impact on the model that triggers something to happen or not to happen. I don't know, how do we say it up here? It's like an all or nothing, but it's a you use this, you don't use it. You select this, you don't select it. You assign this, you don't assign, that kind of a thing. And so it's the 0 and 1s of the binary variables that make that happen, so zeros and ones. In our very first problem, it's gonna be really small. The model itself is not the deal at all. It's what we're gonna learn about using different combinations of binary variables that will help us when we get to the bigger regular problem. And so in this particular problem, you're going to a football game with friends and you don't know who to take, but here's your situation. Your car only holds 5 people, you're one of them, so you're only gonna be able to take 4 of these 6 people that wanna go. Tim and Joe hate each other, so one's not gonna go if the other goes. Sarah and Tom are dating, so if one of them goes, the other has to go. They won't be separated. Fred's only gonna go if both Joe and Tina go. And as a good business student, you're basically just gonna maximize gas money to figure out who's going, right? So you're gonna pick them based on maximizing your gas money. And so that's what we're gonna do with that model. But it is just figuring out all the little combinations of binary variables that we will later apply in a bigger problem. And that bigger problem comes from chapter 6, problem number 93, so in the back of the text. And you'll see it, you can read the problem in the text, but also everything that you need is on that spreadsheet. We'll work that, and then we will make 3 modifications to that problem. It'll take us a little bit. Okay, here's our football gas money situation. So we've got our 6 friends listed here. What you see right below it is how much gas money each of them was willing to contribute. Okay. There's all that. What we're gonna ask Excel to do is put binary variables into these cells saying, 0 or 1. They go, they don't go, they go, they don't go. Whichever it is, 0 or 1. But we did have all those dysfunctional constraints we have to deal with. Okay, the car one is not a dysfunctional one, but the rest is, okay? We do have the car situation. We have the situation of Tim and Joe hating each other, Sarah and Tom dating, Fred only going to these. So we've got to account for those. And so what we're going to do is document some constraints here that will be used in Solver. So for one thing, to figure out that, to make sure that you don't have more than 4 people selected, what could you do as a constraint? Compare something to something.
Less than or equal to 5.
Well, actually less than or equal to 4 because we're going, and so only 4 of the other people can go. Okay, but what? What's less than or equal to 4? You set less than or equal to 4? Well, the sum of that, yeah. So the sum of that range where we are asking Excel to put 0s and 1s in here. These people go or they don't go. If all it was trying to do was just maximize gas money, everybody would go, right? But everybody can't go because the car won't hold everybody. And so we have to make sure that doesn't have to be 4, but certainly no more than 4 1s appear up here, okay? Then no more than 4 people are gonna be able to go. So we sum up the D7 through the I7 and make sure that that's less than or equal to 4. Then we start getting into ones we're gonna have to think about a little bit more. So we've got Tim, we've got Joe, they hate each other, but the combinations that could occur would be neither one of them goes, Tim goes, Joe doesn't, Joe goes, Tim doesn't, both go. Okay, those are the combinations that could happen, but we've just said that because they hate each other, this is not an okay combination, okay? The both going one is not an okay combination. These are okay, this isn't okay. So what ends up happening at this point is you have to figure out how to do a comparison between binary cells, a mathematical little formula and a comparison to cells, a comparison to constants. You know, what could you do here to make sure those three will happen and that one will not happen? What could you do? So my first thought on these is always to check and see if there's a logical operator that would work. Okay. But if I put an equal in here, these two would work, these two wouldn't work. Okay, that's not what I want. Okay. If I put a less than or equal to, this would work, this would work, this would work, but that wouldn't work. Okay, that one would. Greater than or equal to, that would work, and it's not supposed to. That would work, but that wouldn't work. Okay, that's not going to happen. So just putting, those are your only logical operators that are on your constraints, in your constraint box. So that doesn't work. What could we do maybe mathematically compared to something? What could we do? Good choice. Subtract what? Maybe instead of subtracting, we could maybe add them. I mean, sometimes you have to try several things, but if we added them, this is 0, 1, 1, 2. What could we then compare that to? We could make sure it's what? Because remember, these we want to allow, this one we don't want to allow. Yeah, it can only be 0 or 1, but we've got to use logical operators like equals, less than or equal to, greater than or equal to, so we would just say what?
Sum of 10 and Joe less than or equal to 1.
Less than or equal to 1, yeah. And then that allows these and prevents that, which is what we want, is to prevent that one. So we simply, on one side of this, because we're just documenting it here, obviously we'll have to go into solver later, but we sum up the binary cells that go with Tim and Joe, which would be F7 and G7. So add up F7, G7, sum them. I don't care which way you do it. Make sure that that is less than or equal to 1. So on this side of our little constraint, I have F7 plus G7. On this side, I just have a constant. Okay, I had a constant here, I have a constant here. It's not always going to be the case. That's not always how it's going to work. But that's the way it works on this one. Okay. We have another situation, another friend situation. Sarah and Tom are dating. They won't go anywhere without each other. So basically, either they both don't go or they both do go, but it's not an okay to take one without the other. Okay? So that's what we're left with. We see what we want to allow, we see what we want to prevent. Is there a logical operator that's always what I ask myself first. Is there a logical operator that would work here? Just do what?
I would say equal to 2, but then that wouldn't be right for the 0.
Well, just between the two, before you ever even get to comparing to constants or anything like that, start with the thing that's the very simplest thing to ask yourself first. Is there a logical operator that would work? And we've asked that question last time, and there wasn't a logical operator that would work. But that's the first question I would ask here. Is there a logical operator that would work? That would allow the right things, prevent the wrong things? You only have 3 logical operators. Try them. Yeah. You put an equal. Okay. That works. That works. That doesn't work. That doesn't work. It's exactly what you want. Sometimes it's that simple. Sometimes not that simple, but sometimes it is that simple, okay? And so basically, all we have to do is make sure that, and in here I'll put a reference to either one of them, but I'll put the reference for Sarah, okay? That is equal to, and then have a reference to binary variable for Tom. So on one side of this, there's a D7, one side there's a D7, and I don't care which way they go. That doesn't make any difference, but as long as those two are equal to each other, then it forces them to either not go, both not go, or both go. Then it gets more interesting. We've got Fred. And Fred's only gonna go if both Joe and Tina go. Okay, so here's the combinations of things that can happen. Fred could not go, and there would be all these combinations of none of them going, just Joe, just Tina, Joe and Tina. Okay. Fred could go, and we'd have all these combinations of things, neither of these two, Joe, not Tina, Tina, not Joe. Okay. Okay. So the way it's written, if you look at the text in the PowerPoint, it says it in a more complete sentence. But Fred's only going to go if both Joe and Tina go. So if Fred doesn't go, it doesn't matter what happens over here. Those are all okay. Okay. But if Fred does go, he's not going to go. Yeah, I thought I was going too far up, but that was right. Okay. He's not going to go if neither of them go. He's not going to go if it's only Joe. He's not going to go if it's only Tina. He'll only go if both of them are going. Okay. So now we have what we need here. We have exactly what is allowed and not allowed. So when there's three of them, it's not going to be an easy, is there just a logical operator to go between them? Okay. You really have to stop with three of them, sit around and think about it for a long time. And I'm not going to give you a question that has three of them. It's a lot harder than the questions that just have two, because those are just very straightforward and enough for you to think about. But I am going to just show you this one. If you added this, okay, those are little additions. If you added this, I'm going to put it over here, you'd have 0, 1, 1, 2, 0, 1, 1, 2. You could then try to compare Fred to that. Okay? And I was telling the other class, the very first thing I ever thought of, because there's no logical operator that will just go between these either, and it work and allow and prevent what's supposed to be allowed and prevented. So my first thought one time was, oh, let's just add 1 to all of these, because this would be 2, 2, 2, 2, 1, 1, 1, 1, and say it has to be less than this. It would work, it wouldn't work, it wouldn't work, it wouldn't work, it would work, it would work, it would work, and then it wouldn't work there. And it was like, oh, shoot, that's not gonna work, okay? But eventually, what you figure out is, if you multiply by 2, that keeps that on 0. So all of these will work, okay? This puts it at 2, 2, 2, 2. It prevents, it prevents, it prevents, it allows, okay? And so it gives you exactly what you need. You're not gonna have to do one with 3, but I think it's good to look at it, stretch yourself a little bit and think, how would I make this work? But on this side of the inequality, what you want to do is take the binary variable for Fred, which is I7, and multiply by 2. Because that's what I did. I took Fred times 2. And make sure that's less than or equal to the sum of Joe and Tina. Joe plus Tina. Okay. So on this side, it was the I7 times 2 less than or equal to G7 plus H7. So that got all of the situation in there, all of the drama in there. And now we're going to maximize gas money. How do we calculate maximizing gas money?
Some product.
Yeah, some product of what?
The blue and the red.
The blue and the red, because these are the gas money contribution, offerings here, what they're gonna give you, and there's whether or not they're going. So in other words, remember, that's gonna be assigned in a Excel as binary variables. So if there's a 0, the gas money doesn't get added in. If there's a 1, the gas money does get added in. And the overall goal being to maximize that total gas money. And we go into, solver. And now just get all of this into solver. Okay. Gas money is down here in D14 and we want to maximize it. The goal is to maximize our gas money by changing, well, the light red cells. Right there from D7 to I7. So pretty straightforward. We're maximizing D14 by changing D7 to I7. And as far as constraints go, we do know that we have to get these 4 constraints in here. But the other thing we need to do, and I'll just say on this one, it's probably a really good idea just like to do this first, because then you won't forget to do it, is just add in a constraint that says that those cells right there, those changing cells, D7 to I7, actually have to be binary. So just before I forget to do it, I would be inclined to just say, there, get that one out of the way. D7 to I7 has to be binary. Then I start putting all the other things in there. Add the constraint that says, when I summed up the binary variables, that had to be less than or equal to the 4. So in other words, D9 had to be less than or equal to F9. Add in the constraint about Tim and Joe hating each other, which basically was the cell that added up Tim and Joe. Make sure that's less than or equal to 1. Okay, so D10 has to be less than or equal to F10. Add in the constraint about Sarah and Tom dating. That's now in D11 equal to F11. D11 equal to F11. And the last one, which was more complicated to put in, but it's in D12 and it has to be less than or equal to F12. Okay, so once we had thought through it all, we put it all in the spreadsheet. Now it's just in solver, just a matter of putting it in. This less than this, this less than this equal to this less than this. Because we already thought through them. We already did the work of thinking through them. We have 5 constraints because we have those 4, plus setting the constraint of saying that that has to be binary. So when we solve it, we get a solution where we're going to get $13 for gas. We're taking Tom, Sarah, Tim, and Tina. Which is really sad for Fred, who offered us the most money. Because Fred really wants to go, obviously, offered the most money, but Fred comes with a lot of strings attached, because here's the problem. Fred was only wanting to go, or would only go, if Tina and Joe went. Well, they didn't offer very much money. But that's okay, throw a 4th person in there. Well, you can't put Tim, because Tim and Joe hate each other. You can't put just Sarah, you can't put just Tom. You were stuck with just that. I mean, that was it, if he went. And that's why, even though he offered the most money, he didn't get to go, because in total you could only do the 3 people, and you were only going to get $12 instead of $13. Although he would have more legroom, but that's all. We didn't put that into the solver model. So then the question comes up, how much would Fred have to pay if he really wants to go to the game. So how much is Fred going to have to give us in gas money in order for us to include Fred in the set of people that's going? Well, we would do what any good business major does and go run solver table to figure out how much Fred needs to give us. And when we run solver table, think about what you're doing. What is the input cell? What is the thing that you're varying?
I5.
Yeah, I5. Because I5 is, of course, put in there, that's Fred's gas money. Okay, that's how much Fred's willing to pay. That's the thing we're going to vary. We want to see how much, he'd have to pay in order to be able to go. Where would we start?
9.
Yeah. And we go up to,
13.
yeah, 12, 13, yeah. That's good enough. In increments of $1, we don't want them bringing us change. We want them bringing We can go from 9 to 13 in increments of $1. And what's the output cell that answers the question of whether or not Fred's going? D14 is the money. I7. I7 is the cell that has the 0, he's not going, 1, he is going in it. So that's the one that actually answers the question. Now, if you also want to see the money, you can, okay? You can throw that in as extra thing, but it doesn't answer the question we're asking, which is how much does he have to contribute for to be able to go? So we're taking I5, that's Fred's gas money, going from 9 to 13 in steps of 1, and looking at I7, whether or not he's going. Okay. We click OK. And apparently, Fred's gonna have to bump it up to $11. Now, this is kind of interesting, because if Fred contributed 10, we'd also be at $13, just like we are now, okay? When there's more than one optimal solution, you know, they come up with the best thing that's tied, they're both the best possible you could get. I don't know exactly why it uses one versus another. Is it the solution it got to first? Is the solution it got to last? Is it, you know, I don't know. So that was kind of a toss-up. But if he wants to be assured that he can definitely go, then he's gonna have to give us $11. That's what it costs to put up with Fred, apparently. Anyway, so that's the answer to the question. But this is a silly example to learn that stuff, to learn those binaries, how you can make things happen and not happen, little binary constraints. I'm not gonna ask you a 3-way one, okay, I'm only ask you 2-way, but you will have to do it. But where you'll have to do it is at the end of a bigger actual binary problem. Okay, this is a binary problem, but it's not very, you know, it's just doing this and nothing more. We want to see how binaries fit into a real model and how it makes things work. Okay? So when we do problem 93, which is in the back of the textbook, let me just kind of walk you through this a little bit. We buy 8 different products from 5 different suppliers. It would have been simpler if they'd just said, here's the price of this product from this supplier, but they didn't, okay? They told us the list price of the product. Every supplier gives a different discount on every different product, okay? And so whether we want to or not, we have got to calculate the costs, because we don't have the cost. We have the list price, we have the discount, but we don't actually have the cost. How much does it cost to get product 1 from supplier 1, okay? So we'll have to make little calculations in here to figure that all out. Okay, so that's just gonna be a necessary step in this model. It's just a necessary step, has to be done. Then, Excel is gonna be filling in whether or not we use the supplier, and then how much of each product we get from each supplier. Okay, so that's what Excel is gonna be filling in. Do we use them or not, 0s or 1s? How much do we get from any given supplier? And one of the things that we will need to make sure is that we get all of the product that we need, okay? Gotta get everything that we need. So what we get has to be what's required. We're also going to need to make sure that what comes out of the supplier that we get from that supplier is less than or equal to something we're gonna refer to as an effective upper bound. We'll talk more about that later, but let me explain some of this other stuff. For one, we have a company policy that you can't get more than 80% of one product from one supplier. We don't want to be so attached to one supplier that if they did something crazy and they raised prices, that we don't have a relationship with any other supplier that we could get the stuff from. So that is a company policy that we've got right there. Don't get more than 80%. So we're gonna do a little calculation here of how much could you actually get of product 1 from supplier 1, of product 5 from supplier 2, of every one of these, okay? How much could you actually get? Well, what you can actually get would be 80% of what you need, because that would be the max, or we're not, company policy will not allow you to order more than 80%. But we're gonna fill this grid in, and it's shaped like this, so that it can constrain how much we get of each product from each supplier. Then we have some costs that we have to deal with. Well, one, of course, would be the very obvious, the purchase cost. You know, how much are we paying for the product itself? And so that will be a cost we have to pay attention to. But here was another thing, and it was documented up here. There's an administrative cost for using the supplier. It's a $5,000 cost. We incur it if we use the supplier. We don't incur it if we don't use the supplier, okay? So basically, for every supplier we use, we decide to use, and Excel tells us to use, there'll be a $5,000 cost. If we use 2 of them, it'll be $10,000. If we use 4 of them, it'll be $20,000. But that factors in to our total cost, okay? And our goal, our objective in the whole problem is to minimize total costs. But that will factor into it. There'll be purchasing the products, there'll also be administrative costs, and all that together we want to minimize. Okay? Does the problem make sense? We just have to start filling things in. Like I said, it's a necessary thing to fill this in because we don't have the cost. We have list price, we have discount, but we don't have cost. It's just a necessary step for us to fill this in, okay? And so the cost of product 1 from supplier 1, it would be $87 list price, but we're gonna subtract from that 7% of $87. This is one way to do it. 7% of $87. Okay, so that's one way to take B8 minus B8 times E8. Or you could take B8 and multiply it by 1 minus E8. That's perfectly okay too. So whenever we're doing these percent increases or percent decreases, whichever way makes the most sense to you do it, you know, it doesn't matter. But in this formula, I need to make sure, the way I have it, that I need to make sure that there's a $ sign in front of the B's, because I'm not gonna want that to move over, but I will want it to move down. As far as in front of the, and that's in there twice, but in front of the E8, I want it to move everywhere, okay? There's no place I don't want it to move. It's gonna move all around that grid, over columns, down rows, the whole thing. So that's my formula. So instead of it being $87, it's $80.91. For some of these other suppliers, it's even less. I fill all this in. I would randomly spot check in a couple of places. I would move to a cell and make sure that it's referencing the right, cells. Whenever I do the relative and absolute addressing, that's just a good idea. Okay. But that's a necessary thing to have. If they had just given us that, great. But they didn't. Okay, they didn't. So we had to make the calculations, and we came up with our own cost grid of how much it costs for each product from each supplier. So far, so good? We have to make sure that we get all of the product that we require, that we're ordering. And so what are we gonna do in cell, where am I? G22. What are we gonna do in cell G22? Yeah, we're just gonna sum that row. And that's gonna be true for all the rows. We need to make sure that we get all the product that we need, right? We're going to be constraining the amount that comes out of a supplier by an upper bound that I'm gonna refer to as an effective upper bound. And we'll talk more about that later, but just how do we get the total here for, how much came from that supplier? Yeah, we just sum the column. And then we'll know how much came from that supplier so that we will be able to constrain it. Before we go too far though, even on this other stuff, we do need to make sure that we don't allow any order of more than 80, from any one supplier, more than 80% of what's required. So in this cell, where am I, L22, I need to make sure that, and I'll just reference that the 80% is referenced up here in B4. I'm gonna be copying this, and that cell shouldn't move, so that needs to be an absolute reference to it. That B4 multiplied by I-22. Now, the B4 absolutely is not moving. I mean, it's staying on B4. The I-22, I need to put what in order to copy into the rest of this? What needs to be in I-22?
In front of the eye.
Yeah, just in front of the I. Just in front of the I. Okay, I will want it to change rows. I will not want it to change columns as I move across. Okay, and that will get copied across this row and down to the other rows. So what you'll notice is that the exact same number goes across this whole row, goes across this whole row, this whole row. And that's right, because 80% of 592 is 473.60. That's the max you could get from supplier 1, it's the max you could get from supplier 4, it's the max you can get from a supplier. So, but then why do we have to go to all the trouble to make a whole grid out of it instead of just saying, well, here's 80%, you know, just stick with that, there's 80%. Our reasoning behind that is that I want this in this grid so that these numbers constrain these numbers, okay? So that there's this perfect match between constraining those. So that in any given place, that product from that supplier could not be any more than 80% of what we are requiring. Okay. So now I'm gonna put in here to this upper bound. This is what I'm gonna put in. And you're just gonna go with me for right now on this one. I'm gonna sum up these 80% max numbers, because if I think about it, that would be the most you could possibly get from that supplier. Even if from that supplier, you ordered 80% of every one of your products. Because even if you did, that would be the most you could possibly get from that, right there. That sum of L22 to L29. So I'm gonna go with that and copy it across, because it'll copy, it'll copy appropriately across. And we'll come back and revisit this effective upper bound. I now need to start calculating the cost, because the costs go into the objective of total cost. What's my purchase cost? What's purchase cost?
List price and total.
Is it the list price?
It's the sum product of unit cost and maximum quantity.
Yeah, so it's the sum product of we calculated these unit costs, okay, by taking the list and the discount and everything. But those are the costs, and then of course, these are the quantities. We don't know what those quantities are gonna be, but for every, one of these, I'm paying $45.65. For every one of these, I'm paying $37.95. So we calculated that because that's our sum product. How many, quantity here times the actual cost that we calculated there. Okay. What about the administrative cost? How do I calculate the administrative cost?
Administrative cost per supplier times the supplier's share.
Right, so we have here the administrative cost for a supplier, $5,000. We know that for every one we choose is $5,000. I'm gonna make that an absolute reference to that cell. And then we multiply that by what?
The supplier's chosen.
Yeah, well, what we have to do to the supplier's chosen is
Oh,
sum that up. Because in here, the idea is that we're gonna have zeros and ones. Say we choose 4 of them, well then that's gonna be 20,000. So we just choose 2 of them, it's gonna be 10,000. So however many we choose, they're gonna cost us 5,000. Why did I put an absolute reference in there? I'm not copying this cell. That was totally unnecessary. Just force of habit, just to press that up for. Okay, well it doesn't hurt anything, doesn't do anything. Okay, and then real simple, my total cost, just sum these up. Because that's my objective. Because what factors into our decision isn't just what's the lowest cost product, it's balancing that out with the fact that if I use the supplier, I'm paying $5,000, so their stuff better be pretty cheap. Otherwise, I just will shift over and use what I'm already using, you know, cause they have other cheap you know, it's all beyond what we could do figuring it out ourselves, but anyway. Okay, everything's on the spreadsheet. We head to Solver. Our objective is to, minimize cost. So we're trying to minimize B36. So minimize B36 by changing, okay, let me tell you about these changing cells real quickly. A lot of years ago, we figured out the quirkiest little thing about this problem. And that's that if you, that in order for it to work all the way to the end, because we're gonna make a whole bunch of different iterations of running Solver, because we're gonna keep adding stuff to it, you actually have to put in this changing cell range first, hold the control key, and then the other one. Most of you would have probably done that anyway, because it's like, you know, logical top to bottom kind of thing. But a number of years ago, I figured out with somebody whose problem was perfectly right, that when you turn those around, when you get to the very last iteration of stuff that we're doing that Solver won't solve, is weird. Okay, it's just weird, but nonetheless. Put them in like that. It is the two light red ranges, the one that will have the binary variables for whether or not you choose a supplier, and the one that will have the quantity of the products of the different products from the different suppliers. Now we start putting some constraints in. What would you put in first? Yeah, so you don't forget it. It might be a good idea if you put that binary in there. So that's B18 to F18 should be binary. So B18 to F18 binary. And then I know I kind of always have to tell you whether we're going to use these or not use these, and I do on the test as well. You know, use an integer, don't use an integer. On this one, we are going to add an integer to this range right here of B22 to F29, the quantities of the product from the supplier. We'll make that, integer. And I'll let you know when and when not to do that, but we are gonna have that binary on the supplier chosen, integer on the number of products coming from different suppliers. Then we'll start adding in the other ones we see here, which would be what? Yeah, make sure that the total that you get, B22 to 29, is equal to the total that's required, which is I22 to I29. So B22 to 29 equal to I22 to 29. Okay, add another one that's what? Yeah, let's make sure that what comes from the supplier, which is in B to F30, is less than or equal to this effective upper bound, which is B to F32. And what's another one?
B22 to F29 is less than or equal to L22 to P29.
Right, so make sure that all of these values right here, and I know it, like, you don't see this one in the same way, because it doesn't have, you know, not documented in the same way on the worksheet, but make sure that everything in there, all those quantities from B22 to F29 is less than or equal to all of these max possible that you could get from that supplier for that product, which is an L22 to P29. So in total, what you have are 5 constraints. One of them's, one of them's the binary, one of them's the integer, getting the amount that's required, making sure you don't exceed an upper bound, and make sure that these quantities don't exceed 80% of any, on any given one.
B22 to F29.
So Professor,
When you're, yeah,
can you just go back to that constraint, just the maximum.
the last one that I put in,
The maximum one.
B22 to
that's
F29 is
this
all
one
we
right
got.
here.
Yeah, this whole table thing.
Yeah.
Explain
Is
it to
less
me.
than or
Okay,
equal
so
to
B22 to F29, this
L22.
range right here is being
L29.
constrained by what we did over here, where we put the maximum you can get. Let me move this over just a little bit more,
Okay,
so I
that's
can see
fine.
more of this one. The maximum you could get of any given product from any given supplier is this, right? Because that's 80% of what's required, okay, that's 80% of what's required. So everywhere here, if you constrain this, then you're making sure that you're not getting in any one of these spots more than 80% of what is required coming from that supplier. So once you have those 5 constraints in there, and you're minimizing B36, you solve it. Now, the way we just put it in, okay, the way we just put it in, your total cost is $174,270. However, there's a problem. What's the problem?
Didn't choose any supplier.
You didn't choose any suppliers. You didn't choose any suppliers. But you used every single one of them. But you didn't choose them. So there's a little disconnect here. That shouldn't be possible, should it? Because what you've just done is avoid any administrative costs. Because you didn't choose them, so therefore you didn't have to pay $5,000. Well, you didn't choose them because this was a mathematical model that didn't want to add $5,000 in there for every supplier, and it had nothing in there that made it do that. It had no incentive to do that. Yeah.
You could like let it slide and hope we don't notice.
There you go. There you go. Just that's a good solution. But, or we can fix the model. Those are the 2 choices. Well, let's fix the model instead. So this shouldn't be able to happen. Obviously it did happen because there's something wrong in our logic and our thinking in the way that this is set up. We let it use every single supplier, but yet didn't choose any one of those suppliers. So that's not right. It should not be able to use it. It should not be able to use it if we don't choose it. But how would we incorporate that in the model in such a way to make that happen? How can we make that happen? What was allowing us to use these suppliers? I mean, we don't have any constraints on here that we're in violation of, do we? So, like, it let us use all these suppliers here because we didn't exceed the 80%. We didn't exceed the total number of products. So that was letting us do that. What could we put in that area that would prevent us from using it if we didn't choose it? For instance, if we didn't choose this supplier, this upper bound ought to be a 0, right? Like they shouldn't be able to use it if they don't choose it. Okay. Now what could we do? What could we do to that? That's the formula right there.
You could make it if.
But we don't want to put ifs in because we can't really put ifs in and these models run. Okay. And so instead we want to try to accomplish things we would do with if statements, because that's the right thinking, but we want to accomplish things that we would do with if statements mathematically instead, which was the reason for the problem being a binary problem. What could we do that if we didn't choose this, it would be 0? What if we multiply what's here by that cell right there? So if we didn't choose it, there's a 0 there, right? And this is 0. If we do choose it, there's a 1 here, and that number shows up, right? And this is why, I mean, I'll go ahead and put this in, but this is why I kept telling you that this is an effective upper bound. It's not a real upper bound and that it really mattered. what number it was. It was a number that needed to be there in order to trigger the zeros and ones having to be in place in the right places, because this number then would either be 0 or 3,423. You see, it would be a number, a value, or a 0 value or a higher value that would accommodate what you needed. But the reason I kept referring to it as an effective upper bound is that the actual, what number we chose to do here really didn't matter that much as long as it was high enough to accommodate anything we would do, because these values right here, every single one of these values right here, was already being constrained by these, wasn't it? So we never really had to have, oh, you can't order more than 3,423 in here. We weren't going to, because every one of these numbers was already constrained by every one of these numbers. Okay? What we needed this for was what we refer to as an effective upper bound, that it needed to be triggered by the binary variable. Okay? And so in this cell, we take that sum and we multiply it by the binary variable. And what ends up happening is that if we don't put ones up here, this will all be 0, which means you can't use any of them, which means you can't fill your demand, which means this is not gonna run. So it is forced to put some ones in here. It has to put some ones in, 2, 3, 4, however many it decides to spend, it has to put some ones in here. Otherwise it can't order and fill your demand. Okay? So it has to. And so therefore it has to incur administrative costs that it didn't want to incur, but it's a necessary part of it in order to be able to fill your demand, to be able to order and fill your demand. Okay, so once you have that in there, once you fix that, you simply just go back and resolve. And before we actually resolve it, what's gonna happen to our total costs?
It's gonna go up.
Yeah, they're gonna go up. You have to go up. Where, it was never taking those, it was never taking the administrative costs into effect. So at a minimum, boom, it goes up 15,000. But the other thing about it is it now orders some products that are a little bit more expensive than they would have been from somebody else. But if they ordered them from somebody else, they'd have to pay another $5,000, which they don't want to do, which it wouldn't make up for the savings. And so they order a little bit more expensive things and end up just using 3 of the 5 suppliers. Okay. The cost went up a lot, but this model's right, the other one wasn't. The other one wasn't a right solution to it. And this is the part you have to understand, is how that ties in. How that binary is a part of this larger problem that says, instead of us using if statements, instead of that, which is what we're kind of thinking in our mind, well, if you use this, then you have to do this. No, because we can't put those into the models. It's our way of mathematically getting that into the model. That's exactly what it's doing. Because if you don't put a 1 in here, you don't get to use it, that kind of thing. And so, but it does it without if statements, which we can't put into the models. Does that make sense, what's going on right there? Now, I don't think that this is part of the textbook problem, otherwise I probably wouldn't have typed it in on the PowerPoint, but we're gonna modify the model to do one more thing, which is this. What if there was a minimum order quantity of 1,000? Like if you're gonna use the supplier, you have to order at least 1,000 units from them. So let's document that up here. So let's say there's a minimum order quantity, and it's 1,000. Okay, so that's new information, a new modification to the model. So whenever we have something like that, like there's a minimum number of jobs somebody has to do, or there's a minimum, if there's something like that, that actually requires that we sort of modify the model itself here. And here's where I would put it, simply because I like the clarity, the user friendliness that comes from it, and I would not insert rows. I would grab all this stuff, I would Control X cut it, Control V paste it down here. That's all. what used to be there, I pasted down here. And my reasoning for that is because I want the lower bound, which is what that is. If it's a minimum amount you have to order, that's a lower bound.
Wait, so you controlled X?
I control X and then control V once I move down 2 rows, and it just cuts it and repastes it 2 rows down. That gave me 2 rows in order to put in here a lower bound being less than or equal to the supplier. You know, so sandwich the amount that comes from the supplier between its lower and its upper bound. Its lower bound being that if you're gonna use them, you have to order at least 1,000 from them. So what do I put, which is now, for me, in cell B30, what do I put in there as the lower bound for supplier 1?
1,000 times B18.
Yeah, so 1,000, okay, so 1,000, I'm gonna absolute reference that, times what?
B18.
B18, yes, B18. In other words, I don't want thousands going all the way across there. I don't want zeros going out. I want it to be a 0 when you're not using them, 1,000 when you are using them. Okay, so the 1,000 in B5, absolute reference that, times B18, which now I can copy the rest of the way across. So you can see that worked. If we were using them, then we were supposed to order 1,000 from them. We weren't using them. Of course, you can't set that at 1,000, because if you did, you're saying you have to order 1,000 from everybody, and I don't think we're even ordering that many. I don't think we want to do that. We have a constraint right now that's in violation of the one we just put in. I mean, obviously, we haven't run it. You know, I'm not saying it's, yeah. But our model, when it ran last time and we didn't have a minimum, only wanted to order 858 from supplier 2. Unfortunately, we just made a rule that you have to order at least 1,000. We modified the model to do that, and now we have to do what?
Add constraint.
Add that constraint to solver. So add the constraint for that lower bound, less than or equal to what we get from the supplier. So that's a brand new, and if you did it where I did it, then it's in B to F30, less than or equal to B to F32, if you shifted things the way I did. So it's just a new constraint. Okay, it's a new constraint here. What do you figure is gonna happen to the cost?
Stays the same.
It could stay the same, but you're asking it to do something it didn't choose to do in the last mathematical optimization. So it's probably more likely that's what's gonna happen. The cost is gonna go up, and it does. And, okay, now to show you, I don't know if this is what you got or not, but this is not the most precise solution. You remember I told you about the integer optimality? So if you go back into solver right now, you go back into solver, and you go down to the options button. Remember how we talked about the integer optimality that time, and I said, I don't think this comes up again in another problem. I was wrong. It comes up in this problem, where this problem doesn't solve completely to the right answer unless you set the integer optimality to 0. In other words, don't just get within 1% of the best answer, get to the best answer. And this problem's not so big that you can't do that. I mean, there would be problems that would be so big you couldn't do that, but this one's not. So let's change our integer optimality to 0, get to the best answer, and then when you solve it, you actually get 194,048.
Mine was already on 0.
Was it? Because yours stayed like that. For whatever reason, whatever I do in this room doesn't stay, and I always have to keep resetting things.
On the on the tests and stuff, will we have to note to change it to 0, or will it automatically like that?
No, it won't be anything that would change.
Okay.
Yeah, and I honestly didn't even remember this problem did that. I mean, I really did think that most all the problems we did, that it wasn't an issue, but it actually is in this one. It does change it. It's famous last words, but I think this is the last one that happens to it, but anyway.
So I got like all zeros like after entering in that upper bound times the supplier's chosen. Like
When you changed this to
Yeah.
be the sum of that times B18.
They kind of just all went to 0. And I tried like restarting it and doing it all over.
That doesn't make sense.
Cause like before it worked.
Yeah,
without
yeah,
that.
before you had,
Yeah.
when you got the 174
Yeah.
or 3 or whatever it was, yeah. So, I'm trying to think of like what would be a likely thing, and I can't think of a likely reason why that happens. I'm probably just gonna have to look at it afterwards.
Okay.
All right, so here is now we have a lower bound, and again, costs went up just a little bit, not a lot, but a little bit, because we had to order 1,000 from this supplier, which meant we probably had less expensive ones over here that we shifted to order from them because we had to order 1,000, because it was a requirement. Okay, but it's still sort of okay. But then we're gonna add a couple of more constraints, but one at a time. The next constraint is, if you use supplier 2, you must also use supplier 1. Okay, we're using 2, we're not using 1. All right, well, you will have a space on your test where you have a little area to do the documentation that goes with these little add-on binary constraints. So if 2, then 1 kind of thing, is a good way to look at it. But I think what will do that. Two, then 1. Okay, so it's just 2 things. So you just have the usual. Okay. When it says that, don't read any more into it than what it actually says. And it says if you use 2, then you have to use 1. It doesn't say anything about if you don't use 2. Okay, so if you don't use 2, you don't use 2, we don't care. Okay, but if you do use 2, then you have to use 1. So that's not okay. Right there is not okay. But the others all are. So we want to allow those 3 to prevent that 1. And what do I do first? I ask myself, is there a logical operator that would work in this situation? Is there a logical operator that works in this situation? We can't do equal. They work here and here, but not here.
Less than or equal to.
You do less than or equal to, that one's not, okay? It prevents the one you want to prevent, it allows the 3 you want to allow. Okay, so sometimes it is that simple. I mean, sometimes it's not, okay? But sometimes it is that simple. And that's all we have to do is set up a cell. And I still want you to do this in the documentation area instead of just putting it in as a constraint and referencing the cells up there. I want a little documentation area that says, you know, a reference to the binary for 2, that's C18, that should be less than or equal to a reference to the binary variable for 1, that's in B18. I do want a little documentation area that shows your train of thought here on what you were trying to do, but it of course does have to go into solver. Okay, so you go to solver and you add a constraint that says wherever you put yours, you add that constraint. I don't even want to say cell reference because probably all didn't put it in the same place. Okay, but you add that constraint that is making sure that if you use 2, that you also have to use 1. So there's a new constraint, which you are not currently doing, so chances are your costs are gonna do what? Yeah. I mean, it's not that they could say that they're probably going up because you aren't currently doing what you're saying you now have to do. Okay, it's getting a little slow. Well, we opted to just not use either one of them then. We said, forget it. We'll just use 3, 4, and 5 then. But costs did go up a little bit. Yeah.
What values did you use for I-35 and K-35 again?
Down here, I have a reference to the binary for supplier 2, which is C18. And over here, I have a reference to the binary for 1, supplier 1, which is B18. So now we're happy with this solution until we ask the following question, which is, or not, we impose another regulation on this. If you're gonna use supplier 4, you may not use supplier 5. Ah, we're using 4 and 5. All right, that's not good. If 4, not 5. Okay.
I have a quick question.
Yes.
On the 0 to equal, less than or equal to 0 part, I got the same answer. I got 194,048. I put that constraint in and I got the same answer.
You changed your integer optimality to 0? Go ahead and change it,
Yeah,
is that mine?
it's changed to 0.
It is 0, and you still got that?
I'll ask that.
Yeah, that's me, I'm sure. So if you have 4, you cannot have 5. Okay. Again, it doesn't say anything, so don't read any extra into it. It doesn't say anything about if you don't use 4. It doesn't, so we don't care. If you don't use 4, we don't care. But if you do use 4, you cannot use 5. That's all we know. So these are allowed, this one is not allowed. And what would we do with that? I would ask myself first, is there a logical operator that can go between these things and make this work? Greater than or equal to when we're here.
Not equal?
Yeah, well, that wouldn't work on this one, but we don't have a not equal. So unfortunately, that's not one of our choices that we have in that little constraint box. We only have this, equal, less than or equal, greater than or equal. We don't even have a greater than and a less than by themselves in that box. So we only have 3 choices. Less than wouldn't work for that one. So the answer to the question is no, there's not a logical operator that will go in here and work by itself, and that's all. Once that doesn't work, then I shift to things like, can I do some mathematical comparison to a constant? Okay. Could I do some mathematical comparison to a constant? What could I do? So did you just say the sum of 4 and 5? Yeah, so add these up. Well, add them all, okay? And you'd have 0, 1, 1, 2, and now make them less than or equal to 1. And that'll prevent that one and allow the others. And although we said it differently, this is exactly the same thing as the Tim and Joe, whoever hates each other, and they both can't go. That's the same solution set as that, even though we said it in a different way. And that one we basically just said, they both can't go. You know, they hate each other, they both can't go. Here we said, if you use 4, you cannot use 5. Well, that just means that just means they both can't be used. You know, it's the same idea. It's the same idea. It's the same solution as that one, even though we said it a little bit differently. So in here, we're gonna add up the binary variables of E18 and F18 for 4 and 5. Okay. And we're gonna make sure that that's less than or equal to the constant 1. Okay, so E18 plus F18 less than or equal to 1. I've documented it down here. This is the other reason for the documenting it down here kind of thing, is because even though that one could have been done just straight off of these cells, this one can't be. You have to have a place where you're adding them up. So it is better if you just document them. But once I've done that, and you can see I'm in violation of it right now, I go up into solver, I add another constraint. See, by the time this is all said and done, we have a lot of constraints. We add another constraint of the one I just set up. I don't know where yours are on the worksheets. I don't want to say cell references, but I add another constraint to do that if 4 not 5 thing. Got a lot of constraints now. You know, I went from my original 5 constraints to now having 8. But when I solve it, oh, that's the part that if we entered the red cell, changing cells opposite of the way, you know, I told you to put them in there, this is the one where it would just spin and spin and spin forever and not work. And no idea why, because that doesn't really make all that much sense, because it's really not like the problem's wrong, but for whatever reason, it just won't do it. yes, our costs went up. Why? Because we were previously using 4 and 5. So now, because we just kept adding these on, we didn't take any constraints off, we just kept adding constraints to it. Now we're using 1 and 2 and 4, but we're paying $197,000, where we started out around $193,000. But when we started adding minimums, and these two have to be used together, these can't be used together, you know, that kind of stuff, then it messes, well, it raises our costs. That's what it is. Yeah.
You said the changing cells constraint, you have to add one first, like add the large box first?
Yeah, and
or
that
no?
won't happen, on the test either. I do just need you to know on this one, that if you're in that, if you go into Solver, and you're setting it up the very first time, when you put the changing cells in, you do have to select this range before this range, or it breaks down in this last part of this problem. And I cannot tell you why. Really don't know why. Because it's not like it's wrong, it's just for some reason, it's like, it just can't come up with a solution when they're like that. It's whatever order it's doing things in, it just goes and goes and goes and goes. It's kind of odd. But here's the thing about those kinds of constraints, which I realize we learned on the football problem, but we tacked on here. They're a tack on to this other problem. When it gets right down to it, you've got to understand the problem first, because you can't tack these things on if the problem itself isn't even working. And so you really need to understand what goes on in a binary problem. When I say what goes on in a binary problem is how you connect the binary variables to the problem to make it incur, for instance, costs that it wouldn't incur if you didn't connect it. And in this case, and in these problems, that boils down to right in here. Okay, your lower and your upper bounds are tied to your binary because they are your effective lower and upper. And this not really is an effective. The 1,000 is the right number. This number, it never would have mattered. I think on one of the finished file, I summed this up. It doesn't matter on this one. This number matters. But how you tie the binary into your lower and upper bound, that's the gist of this problem. It's what makes this problem work. It's what makes it incur that cost, and that it has to. So you have to understand that before you ever tack these things on at the end. So be careful in your studying that you don't miss that point, okay? Because if you know all of this and you never get this, you never figure these out, you've missed less points than if you didn't understand this, because this is the bulk of the problem, to get the problem done. You're gonna tack on a thing or two at the end, and hopefully you can do that correctly, or give it your best effort, but you really have to understand the problem and the binary and how it works. Okay, so on Thursday, I'm sorry, on Friday we're taking a test. On Thursday, we're reviewing, okay? And I'll get a review sheet out there today, but you know it always just tells you what the problems are. And the problems are the aggregate, the blending, transportation, assignment, chapters 4, chapters 5, and then binary from chapter 6. You'll actually only have 4 of those 5 problems, and we'll talk about that on Thursday. I think that's it. I'll get a review sheet out there. Prepare and be ready to ask questions on Thursday with whatever you don't know. We do have new IAs, and show up, but we have new IAs that should be starting. I have to still say, Chris knows everything that's going on. If you have questions about earlier material, this week it's probably still easier to see Chris, but I did post the new hours. They can help you with some things, but they just started, so it'll be some things they can't help you with. And I apologize for that, but going forward after this test, they're going to be on board and knowing everything that's going on. So
So is he available today?
he is from 3 to 5. He